Picking up where we ended on Monday, we were talking about distillation. So I hope everyone still has their handouts. As a reminder, we have a feed to a distillation column. At the top of the column, we have either a total or a partial condenser. This is our distillate stream. We write D. And then we have a reboiler. Conventionally, distillation columns will have something called bubble cap, where each of these stages looks kind of like this. Where there's lots of these different bubble caps. So what ends up happening as the vapor travels up from a lower stage, it has to bubble through the liquid that is being held on that stage. Now this is tricky to design because if you have too much liquid, the liquid will drain down to the stage below, which is very bad. If you have too much vapor traveling up, it'll blow out the liquid and sort of make an aerosol or a spray and carry that on upwards. Now the reason why that's very bad is the whole point of the distillation column is that down here we have higher temperatures, less volatile material. Up here we have lower temperatures and more volatile material. So coming out of the top is the stuff that's easy to boil, coming out of the bottom is the stuff that's hard to boil. But if I have bulk transitions, right, bulk flow from down to the top or top to the bottom, then it messes up all my equilibrium stage calculations. So stage-wise, we count, at least in this demonstration, I don't know if this is universal, let's say this is stage I, this is stage I minus 1, I minus 2, I plus 1, I plus 2. Now we went over a little bit the different stages. What we're going to do is we're going to do a balance around stage 1. This is picking up where we left off. So in stage 1, we'll draw it out as a box, keeping track of all the material that enters and leaves. Coming into this, we have the liquid 0, which is coming back down from either the total or the partial condenser. We have the vapor leaving stage 1, V1. We have the liquid dripping down on stage 1, and we have the vapor coming up from below, which is stage 2. Now for this scenario, we're going to have infinite reflux. Which means that our distillate flow rate is 0. Meaning we're not taking anything out of the system. Everything that we're putting in, we're just circulating it back. It's called infinite reflux. Now from a total material balance, feed molar flow rate is equal to the distillate plus the bottom. So if the distillate is 0, that means the feed is equal to the bottom. If this is an open steady process, meaning that everything that comes in just comes out, which doesn't mean that we've done a very good job of doing any sort of separation. So in fact, this is all equal to 0. It's a batch system. So essentially with an infinite reflux column, we're charging the system up and we're just letting it circulate through, and we're seeing how many stages of equilibrium it takes to get a certain concentration down here and a certain concentration up here of the different species. So we'd expect an enrichment of the less volatile and enrichment of the more volatile compounds. So in this scenario, the vapors that form at stage 1 are traveling up. So this is effectively V1 right there, right? Which at the top stage, and it's traveling up to the top of the column. It is being condensed and being sent straight back in. So in this scenario, the total flow rate leaving the vapor is coming straight back down as a liquid. So if we do a total balance on stage 1, all of these balances, there's no reactions, no accumulation, no losses. So that means in equals out, so all the flow rates in have to match all the flow rates out. So in this case here, into the system we have the liquid coming down, we have the vapor coming up, and leaving we have the liquid and vapor from this stage. So if these two terms are equal, that means these two terms have to be equal. Meaning that the flow rate coming in and out of each stage has to be constant. And this can be generalized such that L of I minus 1 is equal to V of I, or L of I is equal to V of I plus 1. So every single stage going down has those same criteria being satisfied. Next, we'll do a species balance. Now on the right, this is species K, just so we've got I's and J's floating around. So we'll keep it consistent or clear using K. So in a species balance, it's not the total number of moles, it's the number of moles of species K coming into the system, and the number of moles of species K leaving the system. So in that case here, we have potentially material coming in the liquid and vapor streams and leaving in the liquid and vapor streams as well. So in this case, if we get this right, so this is K, let me look my nomenclature here. Let's see, oh no, that's not it. X, K, 0 times L, 0, plus Y, K, stream 2, vapor 2, is equal to leaving the system X, K, 1, L1 plus Y, K, 1, V1. I think I didn't screw anything up so far. Exercise in nomenclature. All right, so this product here, this is the total number of moles entering the system for species K from this stream, entering from this stream, and then K is leaving in those two streams. So if we apply this same logic here to this equation, what we find is that okay, yeah, I got that right. V2 and L1 are the same. V1 and L0 are the same. So the only way to universally make it so this equation is valid is if the concentrations are also the same going out and coming back. Right? And that's very obvious to tell from here, right? Because if I send out like vapor from the top stage, condense it, and then send it back, the composition is exactly the same. Only the phase has changed. Right? So changing the phase in our nomenclature consists of more or less writing an X versus a Y. Then the same logic applies. If I have the same amount leaving and exiting here, I have to have the same amount leaving and exiting here. And this is how we solve our problems. So generally, we can rewrite this as this will hold true at infinite reflux. And now we will show why this is a neat little trick. So, on the back side of your handout, we have an X, Y diagram. So first what I'm going to do is I'm going to draw out a TXY. So a TXY diagram, again, I'm not joking, every time I draw these I have to rethink. Okay, so component 1 is the more volatile component, which means it should boil at a lower temperature, right? Component 2 is less volatile, and then TXYs kind of look something like this for an ideal system. Okay, low temperatures, which phase am I in? Liquid, high temperatures, vapor. So what's this line here? That's the dew curve. So this corresponds to the vapor concentration. And down here, this is the bubble curve. And it corresponds to the liquid composition. Now TXY is the most appropriate here because we're varying the temperature throughout the column. In general, we don't want to vary the pressure too much because it's going to cause potentially bulk flow. So, the XY diagram. Every point in space on this XY diagram that we're looking at is at a different temperature. So how we construct an XY diagram is we use a TXY that has been solved for all the different vapor-liquid equilibrium conditions. And as every temperature, we have a liquid mole fraction and we have a vapor mole fraction. So essentially, if we were to think about this a little differently, we have temperature, we can measure off of our chart what the liquid and vapor differences are. Now from here, if we really wanted to, and this kind of goes back to, who was at the seminar on Monday? Only a handful of people at the seminar, oh boy. We got to reach you a little bit better. Remember we defined a relative volatility, K, as the the vapor mole fraction divided by liquid mole fraction. This is exactly the partition coefficient that our seminar speaker was talking about with respect to pesticides. I was a little underwhelmed about the rigor associated with the thermodynamics, but I think it's sort of a consequence of the complexity of the system to some extent. But I would highly suspect that very slight changes in soil or very slight changes in plant composition would significantly alter the partition coefficient between a pesticide staying on the earth versus one being volatilized. But anyway, so you could use this information to calculate relative volatility as well, just to tie it back into what we saw from that seminar speaker. So if we construct our XY diagram, So we plot y on the y-axis, x on the x-axis. We have a dashed line that connects, did I get it? Oh, not too bad, kind of straight. Now, in this XY diagram, they will almost always conventionally look a bit like this. Now, why does it look like this as opposed to being underneath this curve? Why do they all kind of look like that?
That's the volatile one.
Yeah, because component 1 is the more volatile species. Let's do it this way. Meaning that in a particular liquid composition, I'm going to have an enrichment in my Y. So this line right here is where X is equal to Y, so it's 1 to 1. So at an azeotrope, which we'll talk about in a moment, this line crosses over. So to solve distillation using an XY diagram, we apply this design criteria. So let's say, for example, we have some composition here that I want to get. It could be X or it could be Y. I'll put Y of distillate here, for example. But if it's a total condenser, right, you know, the vapor and the liquid, vapor and liquid compositions are the same. So I could just put this Z. Right, so this is the composition I want to ultimately get out of my distillate. I draw a line up to here, and this is effectively my total condenser, right, where my liquid and vapor mole fractions are the same. So if I want to count through the number of stages, this curve right here is my equilibrium relationship that ties my liquid and vapor mole fractions together. Meaning that every single time that I have an equilibrium stage here, I'm going to have a dot on my XY diagram. And it works out that the liquid from the stage above is at the same composition as the vapor from the stage below. So how it ends up working out then is if I draw a horizontal line here, I have a meeting point. Let's say this case, this is going to be X of, let's see, do I have this? Let's see, Y of stage 1. Oh, okay, right. This is going to be, depending on how you want to count this, X of, this one here, this is Y of stage 1 is equal Y of X of 1, Y of 1, X of 1. Sorry, here, a little bit confusing. X. 2. Okay, sorry. This is an equilibrium composition where the liquid and vapor are in equilibrium. Then using this Y equals X line, X of stage 1 is equal to Y of stage 2, which allows us to then draw a horizontal line here, X2, Y2. Here's our second equilibrium stage. Draw it down to here. This is where we have X of stage 2 is equal to Y of stage 3. We draw a horizontal line over here. This is our third equilibrium. And so on and so forth. So in this case here, having 1, 2, 3 equilibrium stages, we can get a separation between the bottoms composition and the distillate composition using a distillation column. But the way that I've drawn this one here, this is a relatively easy separation. 3 stages is pretty small. Questions on that procedure? Yes?
Why does the distillate have more fluid, like more liquid composition than the vapor?
Why does, say one more time?
Said that's distillate. Why does the distillate have more of liquid mole fraction than the vapor?
Let me think about this. So the distillate, so the more volatile species, so this here, this is the total composition of species 1 at the top of the distillation column. This is the composition of species 1 at the bottom of the column. So this is a binary, if this is a binary mixture, then this would be, let's say, 95% species 1 and maybe 5% species 2, which is the least volatile species. Down here, let's say it's 10% species 1, that means it's 90% species 2. So you do have a significant enrichment in that. In this drawing here, this is an ideal XY diagram for two materials that are relatively straightforward to separate. So in this scenario here, you're going to have the XY line is always going to be above your Y equals X because it's an ideal system. So even if I did have, let's say 95% of my mole fraction, if I were to vaporize that again, I would get a even higher concentration of that more volatile species to vaporize. Does that help answer the question? So if I could add another stage here, right? I could go up and over, and then if I added one more stage, I would be able to purify to even a higher concentration. In this case, it's an ideal system. In a non-ideal system, which we'll talk about, we'll get pinch points, we'll get azeotropes, and so the separations become significantly more complicated.
So when we're talking about ZD, does that mean that it has that the X1 component, that liquid?
Yeah, let me be more clear. So this is Z1 in the distillate. This is Z1 in the bottoms. Or we could write this as X1 bottoms and Y1 distillate. But in this particular example, because it's infinite reflux, the vapor composition that would come out of the top of the column, now traditionally we would actually want to produce some product. In that case you would want to think of that more as the Y. But in this case here, we're condensing all of it and sending it straight back in. In the bottoms case, we're getting liquid that comes out, but then we're just sending it straight back up and volatilizing it as a vapor. So in this specific example at infinite reflux, the bottoms composition is the liquid and vapor, it's the same. In this particular example. Now in a normal scenario, you would want to have this as your liquid composition and your vapor composition. Is that helping out?
I have a question.
Yes.
These three steps we have in the diagram, are these theoretical plates in the distillation column?
Yes. This is theoretical. So there's a lot of things that can go wrong here. One, getting something to equilibrium takes an infinite amount of time. So we're never going to get a full equilibrium stage out of each one of these bubble caps. There are a tremendous number of tricks that we can do with this XY diagram to help us solve a real distillation problem. So if you can kind of close your eyes and think back to junior or senior year of your undergraduate, right? We can talk about what is the ideal stage to feed your product at. Do you want to feed your material here? Do you want to feed it up here? You can have operating lines that look something like this, where you don't actually get to full equilibrium. There's a tremendous number of little tricks that we can do with this XY diagram to help us solve real distillation problems. When we don't have infinite reflux and when we don't have 100% equilibrium at each stage, but this is not a separations class on how to design distillation columns, so I'm not going to cover that too much. But know that this is the by far simplest approach to tackle distillation. But this can be weeks of time talking about different types of stages, right? The bubble cap, this is something you might see like a plant that was designed in the 1940s. Nowadays, they have much more advanced designs. And a lot of times, distillation columns, they don't actually have individual unique stages. They just dump in like shredded plastic or shredded metal. And that if you have a bunch of shredded junk with a high surface area that's packed in there, you'll have some droplets stuck to it. And then eventually those droplets will kind of dribble down and the gas flows past it. And there's enough surface area that you have some exchange between the gas phase and the liquid phase, hoping to get to equilibrium. So this design is that's a dinosaur design, but it's the easiest one to help us understand. It's the easiest one to help us visualize how the liquid and vapor have to be in contact to get that equilibrium characteristics. But in a scenario like this, we don't talk about equilibrium stages as individual plates, plate 1, plate 2, plate 3. You talk about equilibrium stages in terms of the average height that it takes to approximate an equilibrium stage. So there's a massive, massive amount of information we can talk about on distillation. But this is a nice introduction using the infinite reflux on the XY diagram. Because this is going to be the theoretical minimum number of stages possible. So in any real scenario, if you actually want to produce a product, you have to have more stages. If you have a real material that's actually going to have mass transport limitations, you're going to need more stages as well. So those two combinations means that this is the best case scenario. So back of the envelope, this will work to give you an understanding of how difficult it would be to separate two materials by distillation. But note that this is just by far the starting point. Questions before we move on to non-ideal vapor-liquid equilibrium? All right. So this will get us through most all of the homework. The last problem we have to talk about non-ideal vapor-liquid equilibrium. In this case, we're going to focus most of our attention on low pressure non-ideal systems. So now if I say you have a low pressure non-ideal system, what is our governing relationship for phase equilibrium? Let's start off with our starting point. The fugacity of species I in the liquid is equal to the fugacity of species I in the vapor. Now we could generalize this for liquid-liquid equilibrium, which we will on Friday. But for now, we're still talking about vapor-liquid, liquid to vapor. Non-ideal low pressure vapor-liquid equilibrium. Now, which of the two phases, vapor or liquid, is going to have the biggest consequence of the non-ideality? Liquid. Vapor, low pressure, what does that tell us? Ideal gas. So, partial fugacity of species I in the vapor phase, we're going to approximate it as? Yep. YIP. Now, if we wanted to include some non-ideality, we could do YIP, fugacity coefficient. We're going to say this is equal to 1. So get rid of that, just as a note. Now for the liquid phase, carrying on the assumption, what is the fugacity of my pure liquid if this is a low pressure scenario? Fugacity of my pure liquid in a low pressure environment. Just the saturation pressure. Okay, then I have to include a mole fraction because it's going to be in a mixture. So this would be ideal mixing in the liquid phase. If it's non-ideal mixing in the liquid phase, I have to add in my activity coefficient. So all of this is going to be focused on activity coefficients. Because we've just talked about for the past couple of days all the different fun scenarios that we can construct looking at ideal vapor-liquid equilibrium. TXYs, PXYs, XY diagrams, flash calculations. There's a number of different things, and we can make the problems arbitrarily complex even for ideal vapor-liquid equilibrium. Non-ideal makes it significantly more difficult. So, right now, in less than a minute, what is the bubble pressure equation for a non-ideal low pressure vapor-liquid equilibrium scenario? So take a second and rederive it. So recall, the bubble conditions is when the liquid mole fraction is equal to the total system mole fraction, meaning that we know everything we need to know about the liquid phase. But we know nothing about what's going on with the vapor. So our strategy in is we took this equation where we know nothing. We know none of the compositions of the vapor phase. But we substituted in our different relationships and then derived an expression for what the pressure is equal to, starting with this point here. Who's got it? Most everyone. Okay, good. It is going to look exactly like the ideal scenario, except we're just going to throw in an activity coefficient. This is going to be our gateway into non-ideal vapor-liquid equilibrium.
I have a question.
Yes?
The activity coefficient, that's a function of temperature, pressure, and what's that third variable?
The x underbar, which looks like a T, the way that I've drawn it sideways, x with a line underneath, meaning it's a function of composition as well. Non-ideal vapor-liquid equilibrium can be very tricky. So activity coefficient models are generally only valid for a small temperature range. Otherwise, you have to restart the whole process. So it's oftentimes easiest to look at PXY diagrams for vapor-liquid equilibrium, because changing the temperature significantly is going to change the properties of the interactions. So for a non-ideal distillation calculation, you have to have very good data or a very good activity coefficient model. So this is the composition of my, again, I'm not joking, I have to reconstruct this. My more volatile component, this is the pressure. That means if I have 100% of the volatile species, it will boil sooner, because this is all liquid. Down here is all vapor. And likewise over here, this is the P2 saturation at whatever the temperature of this diagram is. This is pressure 1 saturation at whatever temperature the diagram has been constructed at. Those are the pure species properties. Otherwise, the vapor pressures. Ideal vapor-liquid equilibrium for the bubble curve. Activity coefficient is equal to 1, meaning that this is just a weighted average of the pure species vapor pressures. In other words, it's a straight line. So in an ideal case here, almost. Okay, this is ideal. Ideal activity coefficients are equal to 1. So I can have two scenarios. One where my bubble curve has a positive deviation, and one where my bubble curve has a negative deviation. Which of these two scenarios represents an activity coefficient greater than 1, and which of these two scenarios represents an activity coefficient less than 1? Okay, so let's think about this. I'm a liquid. I'm lowering the pressure. Now normally, I would boil right here on this ideal line. So I start off with all liquid, and I put a vacuum pump on it, or I expand it and I slowly lower the pressure. Now, if I start to boil sooner than I would have normally expected, does that mean my fluids like each other or don't like each other? They don't like each other. They want to run away. So in this case here, the activity coefficient is going to be greater than 1, meaning that there's positive excess Gibbs free energy. Lower the Gibbs free energy, that's the equilibrium scenario. Higher the Gibbs free energy, less likely to exist. So down here, this is where the activity coefficient is going to be less than 1. That these two solutions really like each other. So if we were to look at, so the activity coefficient is somewhat related to the Gibbs excess through, exponential functions and whatnot. So if I have a solution that has large negative excess Gibbs free energy, that means I have either an exothermic mixing process, right? Let's say sulfuric acid and water, salt dissolving in water, in which case those two compounds actually really like each other, and you have a negative activity coefficient. Or you can have negative excess entropy of mixing as well, which is a little bit more conceptually difficult. It's not as simple as does it get hot or does it cold. Likewise, if I have positive activity coefficients, that means I have positive excess Gibbs free energy, meaning it's an endothermic mixing process, or I have really, really weird mixing characteristics. The entropy is a little bit trickier to deal with. Which of these two scenarios is more likely? Activity efficient coefficient greater than 1 or activity coefficient less than 1? Greater than 1 is actually more common. If I grab any two random chemicals off the shelf, almost certainly it's going to be this. Now, oftentimes we actually find ourselves in an environment in the laboratory where we have an activity coefficient less than 1. That's because we tend to work with chemicals that actually can mix into one another. Not a lot of fun chemistry is going to happen if the chemicals don't dissolve. I mean, you can do some cool interfacial stuff, but in general, that's not going to be the case. As a general rule, compounds don't like each other. They like themselves, and when you mix them, the only reason that they mix is because they gain a tremendous amount of entropy. When you gain a lot of entropy, you lower the free energy, and that's what allows compounds to dissolve into one another. So let's say this curve is really extreme, and we get a scenario where we form a maximum. So at this point right here, we have a maximum, or conversely, we could draw it out and have it be a minimum. So the change in pressure with respect to changing the composition is flat. It's a zero slope. Now, counterintuitively, this has some weird products. Yeah, that means if I add more of my volatile species into the system, you would expect the overall mixture would want to volatilize more. But in fact, it doesn't. It wants to stay together. When we have maybe we want to guess, what do we have under the scenario here? This is a azeotrope. Now, I'm not going to go through the mathematics, but effectively, here's an equation for our pressure. If I take the partial derivative of my pressure with respect to the composition of everything in the system, the only simplification that I can make in this equation, what term is not a function of composition in this equation? The pure fluid fugacity. In this case, we've approximated the pure fluid fugacity as its saturation pressure. Mole fraction is a function. All the mole fractions are a function of the composition. All the activity coefficients are a function of the composition. So if I were to take the partial derivative of this expression here, I'm going to have a lot of terms, right? Because I have to have the product rule for every single species in the system. Now, if we go through this exercise, we'll have to end up using the Gibbs-Duhem equation, which is a shame because we're not going to do it, so we can actually see the Gibbs-Duhem equation in action. But if we go through the mathematics, and it's rather extensive, well, not too bad. It's something we could do in a couple minutes, but not worth our time right now. Keep on a couple more pages of notes here for that derivation. We end up with an expression that ultimately ends up looking like this. So we can derive an expression for a binary system we end up with that result. Now, if we relate this to Route's law, if I substitute these expressions here, I solve for this, I get activity coefficient times by the vapor pressure is equal to. If I sub these together, I'll get the mole fraction of species 1 times by the pressure, mole fraction of species 2 times by the pressure. Okay, so this has some fun consequences. Now, conceptually, it's really interesting. It's a little bit counterintuitive. Again, non-ideal solution properties are almost always going to be counterintuitive. Like I said, if you add more of your molar volatile species, that actually just changes how everything packs and interacts together, and it actually somehow gets more stable of a fluid. Same thing holds true on a TXY diagram. They're just much more difficult to demonstrate because the temperature dependence of all of this is baked into the pure species properties, and also the activity coefficient model. So temperature just makes things significantly more challenging. So another cool thing is at the azeotrope, we can actually use this to tune the activity coefficient model. So if we have an azeotrope, we have for a binary mixture, we have two expressions. So we can actually use the azeotropic composition to tune a two variable activity coefficient model, right? The one constant Margulies equation, which I think we talked about a little bit, that one only has one coefficient, but the Van Laar expression, which we'll be using on homework 6, that actually has two coefficients, the alpha and beta terms. So if you have a fluid with an azeotrope, we can use that information to tune the activity coefficient model. Another way of doing it, if you don't have an azeotrope, is you would just have to measure the vapor-liquid equilibrium at two bulk overall compositions. Then you would have two equilibrium points of x and y, and then you could use that information to solve for your alpha and beta. So we're going to be doing that on the next homework assignment. So how do we break an azeotrope? So what we're going to do in the last few minutes of class, so one other thing is sort of for the homework and to solve non-ideal vapor-liquid scenarios, we're always going to want to start with the bubble curve calculations here. Because once we have this information, we can then substitute it into Route's law to solve for the vapor compositions. And then if you plot the vapor and liquid compositions on the same diagram, you'll eventually get your dew curve and your bubble curve to show up. Now the reason why we don't go opposite, because if we start off here with 100% vapor, all of the non-ideality occurs in the liquid phase. So we would have to then have a sort of a big system where we iteratively guess and check what is the liquid phase composition in order for us to solve for the activity coefficient model to satisfy the dew equation. Is everyone okay on that? So with an azeotrope, if I look at an XY diagram, I'm going to have my 45-degree line, or my y equals x line, x of 1, y of 1. So if I have an azeotrope, that means that at some point, my x and y are going to be equal to one another. So I may have an XY diagram that looks something like this. Now there's lots of different forms of the XY diagram you can have. They'll look lots of sort of tricky different things. So if my feed is, let's say, over here, that means no matter how hard I try to separate this solution, I'm never going to be able to get a higher concentration than my azeotropic mixture. So to give it as an example, so I could count up equilibrium stages. And I can keep on going up there. I didn't draw that very good. Maybe I can draw it a little bit cleaner to highlight the complexity here. But it'll actually look more like something like this. I'll get closer and closer and closer and closer and closer to that azeotropic composition, but I'll never be able to break it. So, how we break azeotropes, there's a couple different strategies. One is we can add something into the system that changes the vapor-liquid equilibrium characteristics. Something that might bind to one of the two species or interact with one of the two species more than the other and shift the activity coefficient model. Right, that's going to be dependent on the system examples. The more common way to break an azeotrope that's more kind of universal is to shift the pressure. So this is in many ways sort of a TXY diagram where we're changing the temperature. But if I were to change the pressure from pressure 1 to pressure 2, that means that the temperature at which everything boils at is going to be a little bit different. So if we go back all the way to single component vapor liquid equilibrium and we look at the Clausius-Clapeyron equation. The idea is that if I swing the pressure, we may be at a scenario here where the relative volatilities of species 1 and 2 kind of have this weird constructive interference where you form an azeotrope. But it is very unlikely that the heat of vaporization as a function of temperature is going to be identical between your two fluids. Now, the only way that's going to occur is if they have effectively identical critical points and identical relative reduced pressures and identical reduced pressures. Right? So how the heat of vaporization changes as a function of temperature to some extent depends on how far or how close you are away from your critical point. At the critical point, the heat of vaporization is 0. So unless you're dealing with two fluids that have almost identical critical points and almost identical heats of vaporization, right, then it's going to be a tricky scenario. But if you're working with two things that don't have that characteristic, if I were to change my pressure, I can move my azeotrope composition either up and down a little bit. So what I can do is if I have two distillation columns, this one operating at P1, this one operating at P2, this is going to have a particular azeotropic composition, this is going to have a particular azeotropic composition. So what will happen under that situation is that I might be able to distill in column 1 all the way up to here. Not quite the azeotrope, but getting close to it, right? Because it'll take an infinite number of stages to get there. Then if I can redo it, shift the azeotrope down here, the new curve might look something like this, in which case then I can continue the rest of the way to pure fine material. So just because the curve is upside down, the same rules apply. Right? This is the y equals x line if we're doing infinite reflux, which we can't if it's having two columns more or less, but this line here still corresponds to the equilibrium composition at each stage. So by swinging the pressure, we can manipulate the azeotrope composition. Doesn't have to be a lot, just a little bit. The more you swing the pressure, the less close you have to get to the azeotrope, because then you can shift the azeotrope composition significantly. But to break an azeotrope, you either have to add in a third chemical, or you have to have multiple distillation columns. Now the complexity associated with this, everything that we're doing, the complexity is all baked into the activity coefficient. How detailed of a model is it? How tedious is it to tune to experimental data? How hard is it to look it up as a function of temperature and pressure? So there's a lot of potential power and insight to having accurate activity coefficient models. And so the book covers a lot more than we're going to go over in class. Right? UNIQUAC and UNIFAC are these combinatorial models where you break down a molecule with how many methyl groups it has, how many benzene groups, how many sulfonics does it have, and then you construct a number for that compound, compare it to everything else, and then it comes up with a fairly accurate activity coefficient. NRTL is non-random two liquids. Non-random two liquids would be good in a scenario when you have non-ideal entropy of mixing. Something like the Van Laar expression or the 1 or 2 component Margulies. Those are probably going to be good if you're only dealing with something that has enthalpy of mixing but not a lot of weird entropy of mixing characteristics. Right? The non-random model corresponds to fluids that have different entropy of mixing. You have regular solution theory, right, which is a fully predictive model based on something called the, what is that term called right now? It's delta, it is the solubility parameter. Right, so tons of different activity coefficient models, but the application is the same. It's all just mathematics, but it's tricky math, right, because these are all typically exponential functions. So it's very, very sensitive to small changes. Any questions? So hopefully this should get you all the way over to finish the homework for Friday. Okay, see you guys then.